Alrighty, so in this video, I'm going to address what matters most with boiling point and melting point. First, I'm going to start off by defining boiling point and melting point. So the boiling point is the temperature at which a liquid turns into a gas, and a melting point is the temperature at which a solid turns into a liquid, okay? So the higher the boiling point or the melting point, that means a higher temperature, the more energy is required, which means molecules must have stronger IMFs that are harder to break apart and therefore need more temperature or more heat, leading to a higher temperature. Now, with assessing differences in boiling point and melting point, there's a hierarchy of things we look for. And the first is the strength of the intermolecular forces, okay? And that is the first step whenever you're given an IMF problem, or a boiling point or melting point problem or an IMF problem. The first step is to always identify the strongest possible intermolecular force in each molecule, okay? And so ion dipole is stronger than hydrogen bond, which is stronger than dipole-dipole, which is stronger than London dispersion forces. Now, and so the way that we can do that is, of course, by looking for ionic charges, and then also going and finding the polar bonds and pulling out those partial positive and partial negative dipoles. Now, one thing we have to keep in mind here is polarity, or polarity specifically in how it's influenced by geometry. So for instance, the molecule H2O, alrighty, we've got two bonds. We have a partial negative and two partial positives on the hydrogens. We have an overall molecular dipole towards the oxygen. And so that's why this molecule is polar and water is able to hydrogen bond, is because those dipoles add towards oxygen. There's an overall charge separation on the molecule. A molecule like CO2, on the other hand, alrighty, so CO2 also has polar bonds within it, but because this molecule is symmetrical, those dipoles cancel each other out. So this molecule is overall nonpolar. So water here can hydrogen bond because it has hydrogens attached to an oxygen. However, and so we can hydrogen bond. With CO2, you might predict that this molecule could dipole-dipole because it has polar bonds, but the fact that the molecule has nonpolar geometry cancels the ability of CO2 to be able to make those dipole-dipole bonds. And so the best a nonpolar molecule that happens to have individual polar bonds can do is form London dispersion forces. Okay, so the identity and strength of a particular type of intermolecular force is what matters most. We only bring in the other factors with two situations. Alrighty, those other factors that I referenced in our lecture videos, so branching and size, they only come into consideration in three conditions. So the first is if you have a tiebreaker. So for instance, if I've got propanol over here and ethanol down here, both of these molecules can make hydrogen bonds. However, if both of them can make hydrogen bonds, what tips the balance towards one being stronger than the other? It's going to be this one here because it has more carbons and therefore is a larger molecule. Similarly, you could make the same argument if one of the alcohols had a branched carbon structure and the other did not. The other situation is if we have a molecule that can only make London dispersion forces. If all you can do is make London dispersion forces, then size and the relative degree of branchedness comes into play. So for instance, the molecule on the right, if all we have to deal with is London dispersion forces, that molecule on the right over here is going to have a higher melting point because it can nest nicer than this branch molecule, which has less surface area available to make London dispersion forces. But again, this really only becomes a big deal when London dispersion forces are our primary factor, or a secondary factor that's a tiebreaker between two molecules that can hydrogen bond or dipole-dipole already. And those other factors, as we would call, are branching, which is an inverse relationship with the boiling and melting points. So if you increase the branching, it decreases the melting point and boiling point. The other consideration is size. That's directly related. So if you increase the size, you increase the boiling point and melting point. And finally, as one more thing, a reminder that these factors here are not as important than the strength of the IMFs. And again, they really only come into play as a tiebreaker or when London dispersion forces are the only option. So I'm going to put here secondary to indicate that they're less important than the strength of IMFs or the identity of the IMFs.